We have a function f, which is a function of 3 variables, and it is given by natural log of x squared plus y squared plus z squared. So using this function, we need to show 1 and 2. So we will begin with problem number 1. So in problem number 1, we have to, let's begin with the second partial derivative of f with respect to z and with respect to y. This simply means that first we will begin by considering f and take its partial derivative with respect to z, and whatever value we obtain will again take its partial derivative with respect to y. So let's begin. So we are given here the function f, which is the natural log of x squared plus y squared plus z squared. Right. Now we'll take first the partial derivative of our function f with respect to z, which will be equals to partial with respect to z of log of x squared plus y squared plus z squared. Now we know that the derivative of the logarithmic function log of x is given by 1 over x. So we'll use the same formula, and this will give us partial of f with respect to z. This will become equals to 1 divided by x squared plus y squared plus z squared. Now we'll also need to multiply it to the partial with respect to z of x squared plus y squared plus z squared, which is obtained as a consequence of applying the chain rule. So that means we now have 1 over x squared plus y squared plus z squared. So this will get multiplied to partial with respect to z of x squared plus partial with respect to z of y squared plus partial with respect to z of z squared. Now whenever we're taking the partial derivative with respect to z, x and y will be treated as a constant. So that means this term and this particular term, the derivative will be 0. We'll be only left with the third derivative, and partial derivative of z squared will be simply 2z. So we have 2z divided by x squared plus y squared plus z squared. So this is the partial derivative of f with respect to z. Now what we'll have to do, whatever value we obtain, we'll again have to take the partial derivative with respect to y. So let's do that. Now we will take the partial derivative on both sides with respect to y. So we're partial with respect to y of partial of f with respect to z, which will be equals to partial with respect to y of 2 times z divided by x squared plus y squared plus z squared, which will be equals to, now since we are taking the partial derivative with respect to y, we can consider z to be a constant. So we have 2 times z. That will be multiplied to a partial with respect to y of x squared plus y squared plus z squared raised to the power of -1. Just we have done is taken the expression in the denominator to the numerator so that we can easily apply the power rule. So that means we now have -1 times x squared plus y squared plus z squared whole raised to the power of -1 minus 1 multiplied to partial with respect to y of the inner expression within the parenthesis, which is applied as a result of the chain rule. So that's now going to give us -2z multiplied to x squared plus y squared plus z squared raised to the power of -2 multiplied to, so we'll have to take the partial of x squared, y squared and z squared. Now partial of x squared will be 0 and partial of z squared will also be 0. We'll only have to take the partial of y squared with respect to y, which will be 2y. Now that means we will finally get the second partial derivative of f with respect to z and y. That will be equals to, so the -2z and positive 2y will give us -4zy, which is divided by x squared plus y squared plus z squared whole squared. Fine. So this is what we were asked to show. So this proves the first part. Now coming to the second part, what we'll do, we will multiply this expression with x. So we'll have x multiplied to second partial derivative of f with respect to z and with respect to y. So this is going to give us -4 multiplied to x y z divided by x squared plus y squared plus z squared whole squared. Now, so what we'll do, we'll consider our given function f, which is equals to log of x squared plus y squared plus z squared. we can take its derivative with respect to y, and then we will take its derivative with respect to x. When we do that, we will get the value negative 4x y divided by x squared plus y squared plus z squared whole squared. What we have to do is follow the same steps as we have performed in part 1, and this is exactly the result that we will obtain. And what we'll do, we'll multiply both sides. After we obtain this, we are going to multiply both sides of the equation with z. So that means we'll have negative 4xy z. Similarly, we'll consider the function f and we'll take the derivative, partial derivative of f with respect to let's take it with respect to x first, and then we will take its derivative with respect to z, and this is going to give us negative 4zx divided by x squared plus y squared plus z squared whole squared. And what we'll do, we'll multiply both sides of the equation after obtaining the second order partial derivative. So this will be equals to negative 4zx y. So here we will see here that this term and this term, they are all equals to each other. Hence we can say that x times second partial derivative of f with respect to z with respect to y, that will be equals to y times second partial derivative of f with respect to x with respect to z, that will be equals to z times second partial derivative of f with respect to y and with respect to x. They're all going to be equal to each other, and they're all going to have the value negative 4xyz divided by x squared plus y squared plus z squared whole squared. Hence, this proves the part 2 as well.